I'm going to do a super quick kind of like what's most important this time, and then I'll go into more detail. So let's see. For chapter 4, the most important things would be knowing what each of Newton's three laws says. And the main one that you will have to do any math with would be the second law. So that would be the process of drawing a free body diagram based on a problem you're given, finding the components of all of the forces on that free body diagram. You could use that table for that if you prefer the table. Then you set those equal to mass times acceleration in the x and y directions. Then you decide if it is actually accelerating, and if it is, then you really are working with the second law. If it's not, it's technically the first law, but just set acceleration equal to 0 in that case, and then you solve for any unknowns. That's the main math kind of problem you would have out of chapter 4, and so you can expect 2 or 3 of those involving different forces. So the last thing would be just knowing some of those basic characteristics of each force. Gravity is mass times g, 9.8. I will not have that full general version of it on this exam, which is the law of gravitation. So this version will not be on there. You just need to know weight is mg, mass times 9.8. For tension, the main thing to know is just that it acts along the rope and on the object that the rope is attached to. That's how you'll know how to label it for a free body diagram. For normal force, it is always perpendicular to a surface. That is what normal means. And so it does not always have to point straight up or down. If you're on a ramp, then it will point perpendicular to the ramp. The other thing to know about it is that it is not always equal to the weight of an object. For instance, on a ramp, it's not. It is actually less than the weight of the object, and so it can vary. You cannot automatically set it equal to mg. That's not always true. That's something you prove through a process like the ones we did for each of these cases. So if other forces are acting, we found that the normal force is not equal to weight. If the object's accelerating, then the normal force is not equal to the weight. If the object is on an incline, the normal force is not equal to the weight. So it's one that's the main thing to be careful about, is you cannot guarantee until you prove it to yourself through a free body diagram that those are equal. Friction, 2 types. There are static and kinetic. And the main things to know there are, for static, it can be anywhere up to its maximum value. You would know it's the maximum value if you hear on the verge of slipping or some other phrasing like that. You would know that you're dealing with kinetic friction if you instead see the phrase sliding along a surface. And for either of those cases, maximum static friction or any sort of kinetic friction, you would know that you can use this formula, the coefficient of friction times the normal force. A common mistake I see is I give you this in an exam and you assume that that's this. In other words, you put whatever number I gave you, like 0.3 or something, into your table of forces, when really you have to take that number and multiply it by the normal force. Okay, so for chapter 4, that's the main stuff. Know Newton's 3 laws, be able to apply them with a free body diagram to find out something about an object. Its acceleration, a certain force we don't know, whatever else. There's a lot of ways that problem can go, but it's the same process every time. For chapter 5, the main things to know are the directions of velocity, acceleration, and force for something moving in a circle, and all of that is summed up in this picture right here. So velocity is tangent to the circle, meaning along it. Acceleration is towards the center, that's the centripetal acceleration, and the net force is also towards the center. So if you have something moving in a circle, it's continuously being yanked back towards the center. That's what keeps it on a circle rather than going the way it would like to, which is often a straight line. Otherwise, let's see how to calculate the centripetal acceleration, which you're given right here. It's the speed of the object squared over the radius. That's an important calculation that you can expect to do somewhere on the exam. And then one special case of it. So probably the most likely one to expect is something about satellites. 1 or 2 questions there. One maybe conceptual, one more calculation, but there are only 2 calculations that were even done for satellites, which is that one and this one. The first one is the speed of the satellite. The second is the time it takes for an orbit, the period of the satellite. So if you recognize that that's what the problem's asking you about, you know to jump to these equations. It's a short chapter, so that really is it. Just a centripetal force type of problem, which direction stuff acts, and maybe calculate a centripetal acceleration somewhere. Banked curves will not be on there, so none of that's on there. And then chapter 7, impulse and momentum. So for this one, really the first important thing is the relationship between impulse and momentum, which is the impulse momentum theorem. Can you apply this to calculate, for instance, the average force acting on something? And so it's really more important to know it in this form. I give you some information about some object that hits something else. I want to find the average force acting on it. A question very similar to this one with the baseball. Next important thing is when momentum is conserved. The law of conservation of momentum. Applying it is important, but you also have to know when it applies. And that's going to be if you have no net external force acting on your system. You can have internal forces, which is what collisions are, but you can't have stuff from outside the system affecting it. If you do, then the momentum changes, and the best you can do is the impulse momentum theorem. You can definitely expect calculations like this, and also the one with the bullet on the next page, where the only special thing is recognizing that if two things stick together, they have the same final velocity. And again, I apologize if you're hearing the whole whatever's going on outside for homecoming. But anyway, this last page is also not important for the exam. And one final thing, sorry, is the distinction of different types of collisions. Elastic, inelastic, completely inelastic. What is the difference between them? And you could say that in terms of kinetic energy or in terms of heat, or for completely inelastic, that's the only one where they stick together. But in all cases, the momentum is conserved. So do not forget that. When we're talking about collisions, momentum is conserved. It's the energy bit that's different between each type. That is all the main stuff. So what questions do y'all have?
I have a question about the practice exam.
Okay.
It is question number 7.
Question number 7. So Newton's third law is the one that says if you have a force that object A exerts on object B exerts a force back on object A of equal size, but in the opposite direction. How you recognize those pairs of forces is A acts on B acts on A. That is always the action-reaction pair. So in a question like this, it's asking us, where do you have A acts on B and B acts on A? And that's why I underlined these and said, well, the force the Earth exerts on the book, number 1, that is the force the Earth exerts on the book. And so if there were a reaction pair to that, it would have to be the force the book exerts on the Earth, which is number 4. So those do happen to be an action-reaction pair. The force the table exerts on the book is not an action-reaction pair with the force the Earth exerts on the book, because it's not A on B, B on A. It's, A on B, C, a third thing on B. So that doesn't check the boxes. 2 and 3, like I wrote here, also do actually check the boxes, though. It's the force the table exerts on the book, the force the book exerts on the table. That is still of the form A on B and B on A.
So it's just like the main forces.
The main forces? What do you mean by that?
Like A and B.
Yeah, as in like action-reaction pairs are always of that form. So I'm sitting in a chair right now. The force I exert on the chair by sitting on it is equal and opposite to the force the chair exerts on me. Neither of those is my weight. They're just me pushing on the chair, chair pushing on me. I exert a force on the earth because it exerts a force on me. That's an action-reaction pair. If I push backwards to scoot back out of my chair, then I'm pushing on the floor. It is pushing on me. That's action-reaction. Does that answer the question?
Yes, thank you.
Malak, Shahad, or Zaina, do you have any questions?
I don't have any questions now.
Yeah, me neither.
All right, this might be a pretty short review then. Laura, did you have any more? Okay, if there's no other questions, then I will see y'all next week. The exam is not until next Friday, so we'll just continue with chapter 6 until then.
Esther. My mic was not working. I didn't have any questions.
Okay. I will see y'all next week, and enjoy your weekend. Enjoy homecoming if you're participating.